If you've ever, like, played a modern video game or clicked submit on some web form or even just seen that little autosave icon pop up while you're typing an email. Well, you've seen event-driven programming working right there. It's kind of the hidden engine behind almost every app that feels responsive.
Hmm.
You know, Basically, what we're diving into today are programs that don't just run from top to bottom, step by step. No, they sort of sit there,
Mm.
ready, waiting for something specific to happen, to click a message, maybe a timer running out, and only then do they actually, react. Think of a really good waiter who knows exactly what to do when you ask for something.
That's a great analogy. Yeah, and today we're really going under the hood, looking at that engine. This deep dive, it isn't just about saying, oh, that's an event. We're going to properly dissect the core structures, the actual mechanics of this whole paradigm event-driven programming, or EDP. And crucially, we need to weigh the benefits against the significant trade-offs developers wrestle with constantly when they use this model.
Okay, right. Let's unpack that then, starting with the basic structure. The
Yeah.
sources we looked at highlight, three main components that make EDP possible. First up is something called the main loop.
The main loop, yeah. That's absolutely fundamental. It's what gives the program that feeling of always being alert. You could picture it like a security guard who's constantly watching the front door 24/7. It's this, technically infinite process that's always checking if anything new has happened.
Okay, wait a second, though. If EDP is supposed to be efficient because it's not always running calculations, how can an infinite loop constantly checking be efficient? Isn't that contradictory?
Ugh, that's a really good question. And it gets to a common misunderstanding about the main loop. You see the conceptual code, like, while a program is running, check for events, handle events, right? That makes it sound like busy work. But in, modern operating systems, that loop is usually super optimized. It hooks deep into the OS kernel. It's not burning CPU cycles constantly checking. It's more like it's sleeping efficiently. It waits for the OS to tap it on the shoulder and say, hey, wake up, a mouse click just happened. It's built for waiting, not for frantic checking.
Okay. That clears it up. So efficient waiting, not busy waiting.
Yeah.
Got it. Now, moving from the alert system to the actual response system, callback functions. These sound like promises the program makes.
Exactly. A callback function is basically an instruction you leave for later. You're telling the system, look, when this specific event occurs, I want you to run that piece of code.
Hmm.
This whole process is often called registration. You register your intent.
Right, and the simple registration example makes sense.
Yeah.
Something like button dot on click, button clicked. So the button click function doesn't run immediately.
Nope.
Is it just put aside, ready to go, only if and when someone actually clicks that button?
Precisely. It's on ice until the trigger event happens.
Hmm.
And closely related to that response structure are subroutines. These are super important because, events can trigger some pretty big, complex sequences of actions. Think about clicking purchase now. That's not a small thing.
Definitely not just one line of code.
Not at all. So subroutines are there to break that complexity down into manageable chunks. If your main event handler function is, say, def process checkout, that function acts more like a conductor. The actual work, the detailed stuff, gets done by smaller, focused subroutines it calls. Maybe validate payment, then decrement inventory, and finally send confirmation mail. They handle those specific atomic steps. It stops the main handler from becoming this massive, unreadable beast.
Okay, so I've got the skeleton, the always alert main loop, the waiting callbacks, and the helpful subroutines breaking things down. But what actually makes things happen? Let's shift from the framework, the structure, to the actual action, the features and the mechanics.
Right. The action always starts with events. And let's be clear, events are just occurrences, things that happen. They're the stimulus. Could be a user doing something, pressing a key, tapping a screen, or it could be something internal, like a network message arriving, or even just a system timer finishing its countdown. They're the whats.
And if events are the what's, the nouns, then the event handler must be the how, the verb. It's the specific set of instructions for what to do when that event happens.
Exactly. The handler is the code that executes immediately when an event of a particular type is detected and processed by the loop. Think about a login screen again. The event is the user clicking the login button. The event handler, maybe called something like handle login attempt, then runs the sequence, check username password against the database, then maybe call a subroutine like login successful or shower a message. It's that predefined immediate reaction.
And the piece coordinating all this traffic, making sure the right event gets to the right handler, is the event loop itself. You called it the dispatcher earlier, which seems fitting.
Yeah, the event loop is really the core delivery mechanism. It's constantly watching the queue where events line up after they occur. When it pulls an event off the queue, it looks at it, figures out, okay, which handler signed up for this type of event, and then it dispatches the event to that specific handler. Our source materials often show this basic logic, while true event agrees get next event, if event dot type equals network message, process data, it's just listen, check, route, listen, check, route.
Okay, now this next part sounds really interesting, service-oriented processing. This feels like taking that idea of small specialized reactions and scaling it up to the whole application architecture. How does that work?
That's a perfect way to put it. Instead of one monolithic program trying to juggle everything,
Yeah.
you break the application down into these independent, self-contained services. Think of them like different departments in a company, each with its own specialty. So you might have a dedicated inventory service. Its only job is to listen for events related to stock changes, like item purchased or new stock arrived, and update the inventory database accordingly. Then you might have a separate email service that only listens for send notification type events. The beauty is this incredible modularity and resilience if, say, the email service crashes for some reason.
The rest keeps working.
Exactly. The inventory service, the payment service, they can often continue functioning just fine because they're decoupled. They communicate purely through sending and receiving events, not direct calls.
That modularity does sound like a huge win, but it seems like it all hinges on knowing when things should happen. Which brings us neatly to timing and triggers. We touched on time-driven events, things that happen after a delay or at a specific clock time.
Right, that's the classic set it and forget it kind of event. You tell the system, set timer, 30 minutes, remind you, sir. The event itself is just the timer hitting 0. It fires off, the handler runs, but crucially, the main application wasn't blocked waiting for those 30 minutes. It's asynchronous.
And then there are trigger functions. These seem less about waiting and more about actively starting something, like pushing the first domino.
Yeah, that's a good way to think about it. A trigger function is just a regular piece of code that, as part of its execution, explicitly creates and injects an event into the system's event queue. So if you have a function called, say, initialize a game level, inside that function you might have a line like trigger game start event. It's not waiting for a click or a timer. The program itself is deciding, okay, now's the time to kick off the game start sequence. It lets you blend sequential logic within this reactive framework.
Okay, wow. So we've covered the structures, the loop, callbacks, subroutines and the features events, handlers, the event loop dispatcher, service orientation, and these time-based and trusted events. This whole quite complex paradigm is why your text editor can autosave just when you pause typing, or why chat messages pop up instantly without you hitting refresh. It really does make apps feel, well, alive.
And that responsiveness, that feeling of immediacy, it's the primary advantage developers are usually chasing with EDP. You get much better user interaction, instant feedback. Plus, often more efficient use of resources because, as we discussed, the system is mostly waiting efficiently, not constantly grinding through a list of tasks. And sometimes, because of that modularity we talked about with services, it's pitched as being easier to maintain, at least in theory.
Easier to maintain. That sounds great. Almost too good to be true. But, as always, we need to connect this to the bigger picture and talk about the trade-offs, because this knowledge is really most useful when we understand the challenges, the pain points, and EDP definitely has some well-known architectural headaches.
Oh, absolutely. The single biggest one, the one that causes the most grief, is probably the inherent complexity that comes from inverted control flow. See, in traditional sequential programming, your code is in charge. It decides when to call function A, then function B, then function C. You can read the code top to bottom and see the flow.
Right, redirecting the traffic.
Yeah.
But with EDP, that's flipped.
Completely flipped. It's inverted. The system, the environment, the framework it calls your code, your handlers, based on unpredictable external events happening at any time, in potentially any order. So if you're trying to debug something, track down an error. You can't just follow a straight line. You have to ask, okay, what event could possibly have fired just before this bug occurred? Which handler was registered for it? What was the exact state of the system's data at that specific moment?
That inversion makes debugging significantly harder, especially when multiple events might be happening close together.
And that lack of a clear linear path must lead straight into the next big problem, scattered code. Precisely. If you embrace that service-oriented approach, which has benefits, you might have handlers for a single user action spread across dozens of different files, maybe even different microservices or code repositories. So trying to understand the complete end-to-end journey, say from a user clipping add to cart all the way to seeing the updated cart total, might mean mentally jumping between 5, 6, maybe more completely separate, decoupled pieces of code.
Hmm.
You lose that holistic view, the ability to easily see the big picture flow of the application.
Which must make managing data that needs to be shared between these scattered pieces really tricky. Shared data management must be a nightmare.
It can certainly get hairy. Imagine you have like an order service and a separate notification service. Both might need to know the customer's email address. If they're independent services reacting asynchronously, how do you ensure they both have the current email? What if the user updates their email via a third profile service? How do you coordinate that update across all interested services without causing conflicts, or race conditions where they try to update things simultaneously, or data corruption? It demands really careful design, often involving things like message queues or specific patterns for data synchronization. It's not trivial.
So, okay, we've got hard-to-trace flow, scattered code, potential data conflicts,
Yeah.
and then there's the one developers always groan about,
Uh,
the callback headache.
yes, callback hell. While callbacks are the fundamental mechanism, they can lead to real problems when they get nested too deeply. You end up in situations where handler A finishes its job and its last action is to trigger event B, event B. Event B fires, calling handler B does its thing, and then it triggers event C, which calls handler C.
Oh.
Yeah. When you look at the code, it becomes this deeply nested, indented mess that's incredibly hard to follow visually and logically. Debugging that becomes almost impossible because the actual sequence of execution is tangled up like spaghetti. Hence, callback hell.
And I imagine that also makes testing much harder, because the whole system relies on these external, often unpredictable events.
It definitely complicates testing, yeah. How do you reliably create a test case that simulates a user clicking button X, then typing something while a network message arrives, and then a timer expires, all in a specific, repeatable sequence? You often need quite complex testing frameworks just to mock or simulate that asynchronous, event-driven reality. It adds a significant overhead compared to testing simpler sequential code.
So, wrapping this up, what's the big takeaway? Event-driven programming, it seems, is the engine powering the responsive, immediate feel we expect from basically all modern software, our apps, games, websites. It achieves this by structuring the application around reacting to things, rather than following a rigid preset plan.
Exactly. We've seen it gives us that great responsiveness and often modularity, which is powerful. But we've also established the architectural price can be quite high. That inverted control flow makes tracing logic difficult, the code can end up scattered all over the place, managing shared state is tricky, and debugging those tangled callback chains can be, well, exhausting. Which leads to a really important question for you, the listener, to think about. If you have a large, complex application built on maybe hundreds of these separate event-triggered services where the control flow is inverted like this, how much of your development team's time ends up being spent just tracking down subtle bugs or resource issues? Maybe a handler that leaks memory or never quite finishes compared to the time they spend actually building new, valuable features. That right there is the fundamental tension, the core trade-off of EDP. Gaining that user-facing responsiveness often means sacrificing some internal transparency and ease of debugging. And that's a balance every team using this powerful paradigm has to constantly navigate.